We're going to be starting off today with this. We're making a new project. We're adding our graph component to it. And so in our model package, we're going to add a new file to this. And so right click over here. We're going to go to New, choose File. And it's a C++ file. And I'm going to call mine CTEC Graph because it is that graph data structure we're going to be working on. And of course, we want to make sure we add our header file for it. Go ahead and say Next. It's going to go inside our model folder, model group, making sure we keep those components together. And hit Create. Automatically directs me to the CPP file. We're going to start off as always with our header file because we want to design our code first and then move on. And remember, I am using a namespace for my project. You guys may or may not be, so that's fine. So if you're using one, that's great. If not, just go ahead and put your namespace in there. My namespace is CTEC Data. And then inside my namespace, I'm going to do right up here. We'll do the template and angle brackets, class type, like we've been using all year long. And then class, and then CTEC graph. And so again, because it's a CTEC object, we end with a semicolon right here. And go ahead and save, get our framework ready to go. I am going to add up here, just get that blank line out of the space. And inside our class file, of course, we have our private section and our public section. So we have our two data member sections we're going to be dealing with. We want to make sure we have those files set up so we're ready to go for that. So just FYI, that's where we're going. We're going to start off with our internal stuff as usual. And so in our private section, we have a couple data members we have to deal with. We're going to make first an array of bool type. And so we're making our bool array adjacency matrix. It's going to be of length maximum. And so our maximum is going to be it's going to be a constant. We can tell it's a constant, of course, because it's all caps. We're going to be using the idea of that right here, so we're going to make a constant for that. Right now, it's not going to compile because I haven't written my constant yet. We're going to have in our private section a constant right there, so we can have that be always available for us. And so we have an array of type objects called labels. And our type array is basically just all the things that are inside our adjacency matrix. See? Scratch that. Our labels array of type is all the stuff, the things we are storing inside this graph. This is our data structure itself. We're going to use an array to maintain it though. So we're going to actually be using a combined data structure to actually define this data structure. A little bit different than what we've been doing in previous projects. Just making sure we're not just listening to music as we're doing this though. Hint, hint. And so our many vertices is going to where you do to actually keep track of where we're at on this. So we're going to keep track of how many vertices we have. And so we'll be using this inside our structure. We'll keep track of the vertices, how many vertexes. But we're going to keep up how many nodes are actually inside the graph. So our graph itself is not going to be node-based. So we have over here all these nodes. We've been using this. Notice I don't have my node over here. Rather than using nodes for this one, we're just going to keep track of information using a combined set of data structures. And we're going to do the logic based on that. So that's where we're doing a little bit different here. I don't believe we're actually referencing it anywhere externally. So my static constant in maximum is set to 20. So we have, again, like I said, we have a maximum number right there. We're going to set that for 20. And we have it defined beforehand because, again, just because it's using C++, it reads top to bottom just like we do. And we have to make sure we define that at the beginning anyway. So we have those that data member section set right there for that. We have inside our public section now. We've got to add a couple of components here. So here we go. We're in our public section. So we have in our private section, we've defined our data members that belong to the class. We're making this specifically set so that our graph can only get so big. Unlike our list and our array data structures or our trees, where we have it set so it can get as big as we want it to, with our data structure for our graph data structure, we're giving it a max size. Part of that is for a couple different reasons. One is we're instead of having it where we can actually visually see our data structure as when we look in debug, we're going to be dealing with our data structure mostly by looking at the other data structures that make it up, namely its adjacency matrix, and looking at the idea of our array of labels, aka the components we have inside it. So we have those two different data structures we're going to be dealing with as part of that. So we now need to go ahead and go to our public section, aka the external access, and we're going to be doing a couple new things here in this section. Now we've got our basic framework done, we've got our major save and commit done. The next step we need to do is we need to go ahead and add to this. We have to add the method so we can actually create the components of our data structure. Because the data structure of a graph is basically the idea of a node or a location, aka a vertex, with any edges that are attached to it. So we have a node right here, or a vertex connection that goes to some other node, or a loop connection that goes to itself. We have the idea that we have to build that framework right here. And so our first thing we're going to do is we're going to add a vertex. So it's a void method, and addVertex will be its name because, again, it describes what it is and what it does. Standard rule applies. And then just like we've been using all semester long so far, when we're inserting an object into our data structure, when we put it in, we use it as a const reference value. So that way we have the idea that when we add this to the data structure, we're actually putting in that one, not some changed version of it. And we're using the reference parameter to make sure that happens. So we have a constant reference to that value. The next method we have to add when we're building a graph is we have to add an edge. So we have a void method again. And so with our adding our edge, we have to say which node we're starting from and which node we're ending up at. And so that's where we have our int source and our int target. And I know I've been using the word node, even though we're not actually using nodes. But again, it's the idea of which thing in the data structure we're dealing with, and then which one we're putting it at. So we're making the connection from this one to that one, the source and its target. The next method we have is the exact inverse. We have to make sure we remove edges. Now we're not going to be worrying about removing vertices at this point. We're only going to be removing edges for this. And so if we remove edge, it's going to be the same process. It's going to take two parameters. It takes the which edge is the beginning part of the edge, and which is the ending of the edge, aka which vertices do we end off with. So you have two parameters you have to deal with for that. And then something new, something special. Type, and then a reference, and then the keyword operator, square brackets. C++ is something that allows us to do something we cannot do in Java. We are able to overload the operators. AKA, we are now going to say that the square bracket operator will allow us to get into our data structure vis-a-vis the name of it. So I can say the name of my graph object, square brackets, and put a vertex in there, and it will retrieve that value. So we are going to use the square bracket operator for this rather than use a get for it. So we're going to use the square bracket for this so we can actually get that done. So we're going to use the C++ square bracket method to get access to that data. So we're going to overload the operators for this. This is a little bit different than what we've done before. Notice also that I have an ampersand on here. This is for a reference to the actual value. This will mean that it could possibly change values because we're using that pass by reference approach. So that's going to be very important for us in just a second. Because our next line is the exact same but without the reference operator and with the const keyword. aka we're going to make a copy version. So I can get a copy of the value outside of my graph. So I have the actual value that allows me to change it, and the const version right here, which allows me to copy it. So I have two separate versions to use right here. I also have an int method. This is going to be really weird. Guess what it's going to be? Size.
Whoa!
I know. We're going to have some really strange methods here for this one. We have a method to check to see whether or not an edge is present inside our data structure. And we have also a new feature. And this is where we're going to get rid of some backspace here. So std scope resolution set of type int. And so we're using something a little bit different here. So we're using the standard scope resolution set to refer to specifically the set idea. And so the set, and this is going to be a method that we're going to call neighbors. And I have a red underline of doom right here. So up here, not pound include IOStream, but rather pound include angle brackets set. So we're going to add set to our data structure. And so inside my class, I have my namespace. If you want to keep it, that's great. If not, you don't need it. But I have my template class type. This stuff we have to have inside there. We have our private section where we have our maximum size of our data structure. Again, we're keeping it small for this time of 20. We have our adjacency matrix and our labels array, which is our type array, which tells us how big our data structure is. We have our int many vertices, which we'll be using to keep track of where we are within our structure, how many vertices we have inside it. So we first have the idea of our reference internally for our maximum. So we're just giving that basic reference right there at the top of the structure. And so we have that ready to go. The next thing we have that we need to deal with when we're building our objects is we're going to deal with our addEdge and our addVertex. So we're going to go with, again, our same standard approach with that. So copy. paste that in. It's a void method. And then ctech graph of type. So let's do the addVertex first. AKA, we're going to put something into our data structure. So we're going to start off with the approach we've been doing before. We'll use the assert statement. And so we're going to do the assert as a single statement for this. So we're going to assert that our size is less than maximum. We want to make sure that we are within our size range, that we're not going to actually try and build outside of that. If we are outside of the size range, we'll simply just dump out of it because we don't want to actually build too big. We're going to declare a couple data members for this. So we have int, and this is going to be new vertex number. And so we have our int new vertex number. This is going to be what we're defining for this. We have a vertex number we'll be using. And we are going to set that equal to many vertices. Okay, so our index new vertices is going to be equal to many. Our new vertex number is going to be equal to many vertices, aka it's the number we have within that. So it's an internal reference to where we're at inside there. We're going to update our many vertices data member. So many vertices and plus plus. So we're going to have that many vertices updated by that, so it'll go up by 1. So our internal data structure count goes up by 1 automatically. So we have that reference to it. And now we're going to make a for loop so we can actually go through and check to put this into the right spot. So make a for and then an int. So we're going to loop over our data structure using a single for loop. And so other vertex number is starting off at 0. It's going to loop over until we're at the end of our data structure using that less than. So even though we've already gone up by 1 right here, we want to make sure we get up to and including that last spot. So that's where we're using that one. And then we're going to use inside that, we're going to use our internal reference, our adjacency matrix. And then our square bracket, other vertex number, sub, and then vertex number, or new vertex number. And we're going to assign that vertex to that. And we'll set that value by default to false. When we add a vertex, we assign it automatically to false. And so I'm using both the other vertex number, new vertex number address, as well as the new vertex number, other vertex number address. So I get both spots of the 2D structure. So I don't have to loop over both. So if I'm going over 3 and down 4, I get that one. But I also get over 3 and up 4. So I'm making the opposite direction. So I can make sure I get both spots in my matrix. So I want to make sure that when I add this matrix right here, that every spot's attached to this matrix right here, that this vertex, right here, that every one of them in that is correctly assigned at this point to false. Because I'm adding a new vertex, so that means there is no edge yet been put into play. So I want to make sure I initialize all those to be false. And then my last line inside there, and labels sub new vertex number is going to be equal to value. So my last line I'm going to assign into that into my internal array, my data structure about that. I'm going to assign it that new vertex number, that new spot, the value that I'm keeping track of. Again, remember with the data structure, with a graph, we're designing a data structure that is at its heart multiple data structures. So I have my adjacency matrix that keeps track of where I'm connected to things, and then my internal reference to it, which is just an array, which we're calling labels. Our next method we need to take care of is our addEdge, which means we're making a connection between there. And so this one we have a new assert, and so we'll do a single assert again with this as well. And we want to assert that our source and target are within the right bounds. So assert source is less than, and then size. And that target is less than size. So we want to make sure that when we do this test, to make sure that we're within the bounds of our structure, aka that we're within size itself. And we're adding an edge. We're going to go to our adjacency matrix. And we're going to pass our source as the first parameter, target as its second directionality. And we're going to add that parameter right there from source to target, and we're going to send that to true. So when we have that void method right there, we're adding an edge. We're making a connection between this location, source, and target. We're only making a unidirectional connection. We're not doing like this right here where I add a vertex, where we make them both a false. Because we can have in this directionality of this adjacency matrix, it can only be connecting 1 to 2, not 2 to 1. So if we have it connected both directions, we would call addEdge twice. Because if the idea of this is that a directionality connection, which way we pass the parameters actually matters. So the directionality of source to target matters for the directionality. Notice right here that we are not having any restriction for source and target not being equal to each other, because we do have to provide for the ability of loops. So just as an FYI, we'll be coming to that later. Quick little helper method for that. So we have our addVertex and our addEdge. First thing we want to check to make sure is, again, we want to assert that our size and target are the same. So I'm going to go ahead and copy that one line right here, paste it in there, we're good to go. But then I'm going to declare a variable of type boolean. So bool is an edge, and set equal to false, a default value that we can do, and return is an edge. So I've correctly assigned a variable for that. I've asserted that we're in the realm of our structure. And my last line of code, which is actually the middle line, is where I'm going to assign that value. And I'm going to just say that is an edge equals, and then the adjacency matrix, and I'm going to pass it the source and subtarget. So I declare a data member of the type we're using. I assign it an appropriate value of false to start off. Then I actually retrieve the data structure value from that, from isEdge. I assign that from the data structure of my edges list, of my adjacency matrix. I pass that into the variable, and I return that variable. Now I can do that all, of course, in one line. It's just the idea of having good code structure so I know exactly what I'm doing inside my method. So I have that ready to go all the way through. So we have that isEdge right there ready to go for us. We have those two different operator overload methods. So we're going to start with the reference one, aka the one that affects the actual data that's inside it. So it's of type, and it's a reference parameter, so we keep the ampersand there. And then we give our class name. And of course, since we're our gang sign of type, because that's what we're dealing with right here, our scope resolution, and then the keyword operator, and then addVertex, the one we're going to pass inside that operator. So this is how we actually make it so we can use square brackets inside our data structure. We haven't been doing that before, but this is how we actually would make it so we could do that. We could go through and add this actually to our array project as well. Might be a nice assignment to go back and do. So we are going to return a reference to this variable. So the first thing we want to do, of course, is we're going to assert that the edge at vertex we're being passed actually is within the bounds. So we do assert statements. And we assert that vertex is less than size. Pretty standard right there. No biggie there. And then we're just going to return, and then labels, sub, and then vertex. So we have right here in the reference mode, notice that it's the operator has the reference parameter modifier, aka the ampersand. So for our reference copy, aka the one that will affect or impact the value stored in our data structure, we have the reference parameter. We also are going to make a copy version, one that will make a copy of whatever's stored inside there. So what I'm going to do is I'm going to do this magic thing of copy the entire method, copy, paste, take off the reference modifier, and instead add the const modifier. Okay, so the question was, why would I have these two different versions? And the answer, this is if I want to actually impact or change what's stored inside that. By retrieving right here, it gives me an access to the reference itself. So any changes I make would happen to my data structure. Versus if I call the const version. If I call the const version, I merely get a copy of that value that I could use just to say, for example, for display purposes. This one I could use if I want to change it. This one if I just want to get a copy. And we'll talk more about that as we start dealing more with this in a bit. We now need to talk about the idea of our set. So it's going to be a std scope resolution set of type int. A little bit new stuff. Slightly side digress, but it's very important for the idea of dealing with graphs and other parts of math for computer science. So a set is a data structure or collection. And so because this is C++, it can be any type, whether it be primitive or object-based. In Java, of course, all types are objects. But the set has a couple rules. Rule 1, the first rule of a set, there are no duplicates. So if I make a set of something, I can have all the things I want as long as they're not duplicates. So I can have a set of all real numbers. I can have a set of all even numbers. I can have a set of all odd numbers between 1 and 5,000. It's just the idea of it's everything in that group that's not duplicated. So there's no dupes in a set. So if I have string car and string car with the same letters, same spelling, they cannot go in the same set because they have the same spelling right there. So no dupes at all, no duplication. The empty set is also okay because it's the single empty idea. So I can't have null and null in a set because null and null are the same thing. But I can have a set that just has null inside it. So a set is a type that has a collection of things with no duplicates. In this case, we're going to be dealing with a set of int. So I go back right here. I'm doing a std set int. This is my return type. And so in my return type right here, it's in my class CTEC graph. And my method on this is called neighbors. Again, I have to assert that I'm within my realm of size. So I'll have my standard assert statement. So I'm just going to go up and copy this one right here. I've already typed it a few times. Might as well copy it back over. So I assert my size is within my range. I'm going to declare a set variable that I can return. So std scope resolution set. It's of type int. And we will call this the vertex neighbors. And we're going to make a for loop to go over and add to that. So we're going to do a for, standard approach for a for loop. So if my adjacency matrix at this location, sub-vertex, sub-index, returns true, I'm going to add that index into my set. So only if it's in there will I add it. And so I'm going to loop over the starting at this one. And so my index goes through every single column of that row. So I'm going to use every row, everything with that row right there that has that vertex in it. So everything of row, say for example, vertex 9. Every column inside that row, I'm going to check to see if there is a connection. If there is a connection, I'm going to insert that connection into my vertex neighbors set. I then return it after I'm done. Okay, so we have our template class type, and it's a void method. Okay, our last method is the removeEdge method. Our removeEdge method is going to take out any edges. We're not worrying about adding or removing any locations from this point. This is just edges that connect those 2 points. So the lines, aka, is what we're talking about. Again, we want to keep our standard assert that we want to make sure that our source and target are within a realm. So assert 2D structure, our adjacency matrix, we're going to set that location to false. So I'm going to say that my adjacency matrix sub source sub target equals false. We can assume that we pass that false parameter to that location. So the edge that connects these 2 spots is set to false. There's no longer an edge connecting them. And it's simply a void method, so that's all we have to do, and it's done.